Hello and welcome. This video is a review of Unit 9, Simple Harmonic Motion. So a smaller unit, but we'll do some quick key ideas here. The first topic is going to be on the simple pendulum because it has a pretty repetitive motion. So remember that a simple pendulum is just kind of like a very light string with a mass at the end. It's usually small angles, something like 15 or 10 degrees from the vertical. And remember that one period is the time for one oscillation. So the period is the time for one cycle or one complete movement. In the case of the simple pendulum, the period, which is a capital T for the variable, is equal to 2 pi times the square root of the length of the string, L, divided by G, the acceleration due to gravity. The mass of the simple pendulum and the angle that it's pulled back at do not matter. They do not impact the period at all. So there you have the basics of a simple pendulum. We can also calculate the frequency of something when we know the period. The frequency is the number of cycles per second, and frequency is just 1 over the period. Let's go full screen here. This is a little easier. Other things that I wanted to mention, connection to some other units. Let's see here. Connection to energy. You could be asked to make a graph of the gravitational potential energy of a simple pendulum, or at least interpret a graph of the gravitational potential energy of a simple pendulum based upon one period. This would be half a period, and then maybe 3/4 of a period, and 1/4 of a period. And if we start like my simple pendulum up at the top in the drawing, that has a maximum potential energy to start. And then when it gets over to this other side, which is actually half a period, it's going to reach another maximum potential energy, and then a maximum potential energy when it gets back to complete the first full period. So you have these 3 maximum points. In between those are the low point, which is the bottom, and that's when you're getting 0 potential energy. It's at its lowest point, and this graph will kind of, almost like a sine graph, have a curve to it. If we were to graph the kinetic energy versus the period, if we did those same markings, quarter, half, 3/4, and a full period, the kinetic energy graph would be reversed. You get your maximum kinetic energy at 2 times at a quarter and 3/4, so that would kind of go up and down like this. Also, if you had to do a calculation with the simple pendulum based upon, if you had to actually get some numbers, if this is the angle that it's drawn back to, the potential energy is based off of the vertical height from its lowest point. How do we find this height right here? Well, if the string has a length L, this distance right here is actually L cosine theta. So this height is going to be L minus L cosine theta, because you have the full length. Let's see if I can draw that in green. This full length is the length of the string, and that would be L. And then this length, which I'll draw in red, is the adjacent side to that angle when it's angled back. So that's L cosine theta if we subtract those two. I thought that was a little kind of side note. I don't know if that's, the biggest idea, but it could be useful in some instances. Let's see. I had one more connection that I wanted to do with the simple pendulum. And connection to centripetal and forces. So when we have the simple pendulum, if we were to look at the forces that are acting on it at some angled point, there's going to be two. There's going to be a tension, and there's going to be mg. And we can find the components of these forces. If this is the angle theta, this component right here is mg sine theta, and this component is mg cosine theta, just like an inclined plane almost. If the pendulum is moving, so let's say it's moving at the bottom of its arc with velocity, you should keep in mind that the tension needs to be greater than mg because there needs to be a net force to provide the centripetal force. So we could actually write centripetal force as mv squared over r. Tension minus mg equals mv squared over r. So if we were able to calculate the velocity of the pendulum at the bottom, we could actually work backwards and figure out the maximum tension, which would be at the bottom for this pendulum string. So those are all little connections of the pendulum. Obviously, you need to know about the period and the frequency, but little connections to other things. And one final note, if this wasn't moving, if the pendulum were just to stop, the free body diagram would be different. The tension would equal mg. My mg got lost a little bit there. So the tension would equal mg. So those are some basic things about the simple pendulum. Also in this chapter, we did a spring and mass system. So I'll review that right now. So let's take a look at the spring and mass system at a couple points. We had a really good detailed drawing from our notes, and I think that might be good to look at. So here's the spring, not my best spring, really extended. This dashed line is the equilibrium point, x equals 0. If this is the maximum, right, we'll call this x equals a for the amplitude. That's your maximum stretch. You're going to have a force, and you're going to have your maximum acceleration at that point. That force is equal to k times x. K is the spring constant. X is the displacement of the spring from equilibrium. So we could calculate that force. We could also calculate the acceleration by using F equals ma. If we get to this middle point, if we were to release it from this point on the right, get to this middle point here, just full screen, we're going to have zero force, which means we're going to have zero acceleration, but we're also going to get to our maximum velocity. And that's the equilibrium point right there. And then if we were to go beyond that, which they usually do, it's going to have some momentum that's going to carry it forward. Force is going to be in the opposite direction, pushing to decelerate it. Force and acceleration are linked. They're together. They're in the same direction. We could use energy to figure out what the velocities are. The potential energy is equal to 1/2 kx squared. We could equate that to the kinetic energy in the middle if we want. In between the extreme points, the ends or the middle, we could have a combination of potential and kinetic energy. And this system, because it will go left then right again, it will have a period, and that period is equal to 2 pi times the square root of m divided by k, where m is the mass on the spring and k is the spring constant. Final thing about these systems is that if they're in vertical setup, if we just lower that mass down slowly, we have the force of the spring up equals mg down, so that the velocity is 0. This is what we call equilibrium. This is if we were to just lower it down. So this is the equilibrium point for a system in the vertical setup. If we were to pull this down away from equilibrium and set it in motion, then it would act the exact same as a horizontal spring system. So there's really no difference between the two, and this would be equal to kx, how much the spring was originally stretched. But once we get it to this equilibrium balance with gravity, then we can just set it in motion and you treat it as a horizontal spring system. Back up here real quick. Remember, the period is not impacted by the amplitude. I think that's an important point for simple harmonic motion. For all simple harmonic motion, whether it's a spring mass system or a pendulum system, what you're really looking for is this right here, this force that's always going back towards equilibrium. This force is always going back towards equilibrium. That's what we call a restoring force. It happens with the spring and mass system, and it will happen with the pendulum. There's a force here. It's called the restoring force, and the pendulum's over here. It's a force pulling it back to equilibrium. That's called the restoring force. So there are some basics for the simple pendulum and the spring mass system, simple harmonic motion, and I hope this helps out with this Unit 9.